you. Welcome. Hello, everybody. My name is Sebastian Jordan Montaño, and I am here to present our paper, Evaluation Finalization-Based Object Lifetime Profiling. So, let's start. Let's quickly start about discussing about context and description of the paper. Well, first, we know that object lifetime information, it can be very useful for applying memory optimizations such as pretenuring objects that they can live a long life, or to check the garbage collector parameters to optimize performance. And one way of developing these profilers is through finalization mechanism. This is a technique that it was used in the past, but it was not evaluated in depth. And in this paper, we are going to focus on this. If we want to use finalization to do object lifetime profilers, this is the way to do it. First, we need to capture the allocation time. And this is done through code instrumentation. We can instrument the parts of the code where allocations are produced. And at each time that allocation is produced, we capture this allocation time. And then with finalization, we can capture the collection time. And with these two things, we can estimate object lifetimes. One challenge of doing this, but however, this can have advantages and disadvantages. For example, one advantage is that these mechanisms are normally already presented in runtimes in virtual machines, so we don't have to implement it. But one challenge, it can be, for example, we can have a delay lifetime observation. For example, if we look at this timeline, we have a time 0, the object allocation time, in which is the time in which the object is allocated. Then after some time, the object becomes unreachable. But it's only after some delta that when the garbage collector or memory management is traversing the memory, in which it detects that the object is unreachable, and then it starts to prepare the object. And then after some other delta is when the runtime is actually finalizing the object and is when we are taking the measurement. So as we can see in this little graph, we can see that there is a delta between the actual or the real lifetime and the estimated lifetime. And this delta, it can be as big or little, but we cannot know this in advance. And another challenge, it can be the contamination. Well, in this paper, we focus on ephemerons, that ephemerons are one finalization mechanism. There are others, but in this paper, we study ephemerons. And basically, how do they work is that at each time that we allocate an object of interest, we allocate also an ephemeron, and the ephemeron knows its object. And then the garbage collector detects that the object of interest is unreachable. It puts it into a finalization queue, and then after some time, also the runtime actually invokes the finalization callback to finalize the object. So this can contaminate the heap, adding extra garbage collection pressure. So the goal of this paper is first to understand the impact of the ephemeron contamination, and then also to understand the impact of the delay observation times. For this matter, we developed Philip. Philip is a finalization lifetime profiler that we built for experimentation. It tracks allocation time by instrumenting allocations. It tracks collection time with ephemeron finalization, and optionally also it can pretenure the ephemerons for experimentation. We are going to discuss this point later in the presentation. And finally, it has a built-in sampling support that it can track a configurable subset of all allocations, like the developer can specify the sampling rate of the percentage of the allocations that wants to capture. So now I'm going to pass to the methodology and the results. In this paper, we study 4 research questions that are the first one is our lifetimes, are the lifetime that we are estimating are actionable. The second research question is how does sampling impact the computed object lifetime? This question aims to study the precision. The third one is, does sampling reduce the execution time overhead? And finally, we have if the sampling reduces the memory overhead. For time constraints, we are only going to explain the second and the third research question in this presentation. But if you are interested, please, you can have a look at our paper. In our paper, we have the 4 questions detailed. As the benchmark selection, we selected these 5 applications. First, we have data frame. Data frame is a tabular data structure for doing data analysis. Honey is a physics simulator. Uh, Moby Dick is a multi-agent simulator. Also, we have a block that is a low-level UI framework. And finally, we have Moose. Moose is a platform for doing software analysis. And as the general methodology, what we did is we profiled each benchmark using 4 different sampling rates, 0.1, 150, and 100%. Also, when the results are presented relative to the total execution time, this is to account for the profiling overhead. Instead of saying that the lifetime it will be presented, for example, instead of saying leave 1 or 2 seconds, we will say that leave 15% of the total execution time. And finally, also the execution time overhead will be presented with and without ephemeron pretenuring. So for the first research question that I will present in this presentation, that corresponds to the second research question of the paper, we have the methodology. What we did is we compared the estimated lifetimes across all sampling rates to assess the degree of variation between them. And also we present an in-depth analysis of the data frame benchmark. It is worth to note that even though if we only present in-depth the data frame benchmark, we obtained similar results for all of our 5 benchmarks. So first, we have this table. First, let me explain this table. In the rows, we have each of the benchmarks, each of the 5 benchmarks. And in the columns, we have the overall average lifetime for the 4 sampling rates. And in the last column, the one in the right, we have the average with the standard deviation. So for example, if we can see the data frame example, we can see that for 100% sampling rate, we have an overall average lifetime of 15%. So the overall average, it says that the object leaves 15% of the total execution time. And in the other extreme, we have 14.2%. So if we go to the last column, we can see that we can observe among our 5 benchmarks that there is no such a big variation between the estimated lifetime across all the sampling rates. We can see that there is a small standard deviation, except for the Honey Ginger and Moby Dick. And we can see that for Honey Ginger, the standard deviation is 15%, but the estimated lifetime are really small. We can see 0.09, 0.05. So we have a big standard deviation, but still the estimated object lifetimes are really small. And for the data frame case, for the in-depth analysis, we have these histograms. First, also let me explain. In the top part, the first 3 rows, we have the short-lived classes, in which each histogram represents in the y-axis, it represents the percentage of objects, of allocated objects. And the x, we have the relative object lifetime. So, for example, we can see for the class fraction, the first one in the top, for 100% sample rate or even for 0.1, we can see that 100% of the objects, more or less, they have a lifetime close to 0. This is the case for all the 3 short-lived classes for all the 4 sampling rates. And for the other example, for the long-lived classes, we have the opposite behavior. We have, for example, we can see the byte string class. They have like almost around 100% of the object that they live close to 100% of the execution time, so until the end of the execution time. And similarly, we can observe a similar behavior for all the 4 sampling rates also. So as a conclusion for these research questions, we can see that we can observe consistent lifetime frequencies, and this suggests that our profiler gives precise measurements. As a recommendation for developers, we recommend developers, if they want to use such a profiler, they can start with a small sampling rate, and they can gradually increment it if needed. We obtained precise results using a 0.1 sampling rate. Of course, this also depends on the application that is going to be profiled. And for the second research question that I will present in this presentation, that the third one in the paper, we're going to study the execution time overhead. As a methodology, we did a comparison across 5 configurations. First, we have the baseline, that is the execution time without the profiler. And also we have the execution time with the profiler active with sampling rates of 100%, 50, 1, and 0.1. These are our 5 configurations. And also in these research questions, we studied the effect of pretenuring the ephemerons. For that, we have this table. But first, also let me explain quickly the table. In the rows, we have the benchmarks. For example, in the first one, we have data frame minus pretenuring. This minus means without pretenuring, and the plus with pretenuring. And also we have delta. So the delta is the difference, the overhead difference between the with and without the pretenuring. So as we can see that pretenuring the ephemerons have a positive impact across all 5 benchmarks and across the four sampling rates. As an extreme example, we can see the one in red that for the Moby Dick benchmark, we managed to improve or to reduce the overhead by 15 times by pretenuring the ephemerons. And so as a conclusion, we can see that pretenuring the ephemerons has a positive impact on the overhead, reduces the overhead by 3.68 on average, and the average overhead is 1.89 across all sampling rates. This makes a finalization profiler a practical alternative to estimated object lifetimes. If you like this presentation of our paper, you can find more information in the paper. For first, you will find all the research questions that will be detailed, and also you have the evaluation, the methodology. We also detail results and implementation details. But this was my presentation. As a conclusion, we can say that finalization profilers can be weakly actionable and they can have low overhead. Also, that pretenuring the ephemerons and sampling have a significantly effect on reducing the overhead. And finally, sampling provides relevant object lifetime information. My name is Sebastian Jordan Montaño, and I will be happy to answer your questions, if any.
Thank you, Sebastian. So do you have some questions for Sebastian? We have a moment for a question.
Hi, Sebastian. Sarah here. I have a question about sampling. So is it sampling of the allocations? Is it sampling of the deallocations or both? I think I missed this part.
Yeah, it is sampling of the allocation. For example, in the 0.1 sampling rate, that means that we are only going to take one allocation per 1,000.
And when we say 100% sampling, this means this is the most accurate measurement?
Yeah, 100% sampling rate, that it means that we are going to capture all object allocations.
Yes, so it's not susceptible to any delays from the runtime? Because at the beginning you mentioned that sometimes when we measure, we can be impacted by delays because of the runtime. So with 100%, we shouldn't expect any delays, correct?
So I will go back to this. So yes, you're right. If we capture all the object allocations, that it can introduce overhead and it can potentially increase this delta. We cannot know this by advance, but our experiment suggests that 100% sampling rate also produces like precise results, but it has the disadvantage that it can introduce also a lot of overhead.
Okay. Thank you.
Thanks.
I feel like I must have missed something because the pre-tenure, you showed the reduction in overhead from pre-tenuring the ephemerons, but doesn't that directly mean that we do not trigger those finalizers until later, until major collection? So isn't there a trade-off with the accuracy, but it didn't, is there a trade-off between overhead and precision there, or is it just all a win to pre-tenure ephemerons?
Thanks for the question, it's really good. And no, for the pretenuring of the ephemerons, there is no disadvantage because the ephemeron has a weak reference to the object. So it doesn't change how the object is going to be, when the object is going to be detected by the garbage collector.
Got it. So it doesn't change when the finalizer runs. Got it.
Sorry?
So it does not change when the finalizer runs. Thanks.
Yeah, exactly. It doesn't change.
Great. Well, thank you very much for that talk. And with that, we conclude the session. So thank you, Sebastian.